linear algebraic equations and matrices. So it is important to note that we have to write our equations or in order to implement this in MATLAB, we want to implement our linear algebraic equations if we're going to solve simultaneous linear equations in this form, wherein you should be in the form of k times x and equal to g times m. Okay, so this okay, so this one is your usual n by n matrix. This is a square matrix. This is a vector. An n by 1 vector. G is a constant. And m is another vector. So we must place our solution in this form. Then we can solve this equation using several ways. So one way is to solve this by MATLAB, wherein the vector x, when you still remember your vector algebra, your matrix algebra, the component x or the unknown x or vector x is equal to k times the for matrices, we're going to use the backslash operator to indicate a inverse operation for MATLAB. So this is one way. So that's x equals k backslash g times m. Okay, so that's one way. Another way is we take the inverse of k. So that inverse of k times k would be the identity matrix. And then the other side would be inverse of k times g times m. So this is another way. X is equal to the inverse of k times the product of g and m. So we're going to use this method to solve, let's say, your three particle uh, oscillators. Okay, so what we have here is a coupled oscillator of three particles M1, M2, and M3. The spring constants of the three springs here will be K1, K2, and K3. So here we assume that the masses and the springs are not equal to each other. X1, X2, and X3 are the displacements of M1, M2, and M3 respectively, with respect to their respective equilibrium position. Okay? So as we discussed in our theoretical mechanics class, even if the coupled oscillators are oriented vertically, okay, because of the presence of a constant external force, namely gravity, on each of the particles. So the net result is that the effect of that constant force or gravitational force will just shift the equilibrium position of the three particles. And then, but gravity will not be included in our discussions anymore. But let's say we include the effect of gravity. So that means each particle will experience not only the spring force really associated with the springs connected to it, but as well as the weight of that spring. Okay, so for example, for M1, there are three forces on M1. First force would be the force exerted by K1. So we're going to identify the springs by their spring constants. Okay, so this will be for K1. So the force, the magnitude of the force would be K1 x1. And then below there are two forces. There's a force here, which is K2 times x2 minus x1. So x2 minus x1 is the net displacement of K2 due to the displacement of m1 by x1 and the displacement of m2 by x2. Okay? And then lastly, we identify the gravitational force exerted on m1. So this is m1 g. Same goes with m2. So for m2, we have forces upward and then two forces downward. Okay? So the force upward would be K2 times x2 minus x1. And then downward would be mg2 and K3 x3 minus x1. And then lastly, for M3, there are only two forces because there is, of course, there's gravity that is directed downward. Okay, so this is M3G. And we have the spring force due to K3. So this will be K3 x3 minus x1. Okay, so here we have three particles, so therefore we will have three equations of motion. The three equations of motion are as follows. Number one would be negative m x1 double dot. This is equal to, negative means this is downward. This is negative m1g minus k2 x2 minus x1 plus k x1. For equation number 2, we have negative m2. By the way, this should be m1. Negative m2 x2 double dot. This is equal to negative m2g minus k3 x3 minus x1 plus k2 x2 minus x1. Okay, and then lastly, the third equation would be negative m3 x3 double dot. This is equal to k3 x3 minus x2 minus m3g. Okay, so as I mentioned here, we are going to consider the gravitational force this time. Okay, so if we're going to rearrange this in this form, so you will notice that x1, x2, and x3 are the position functions of m1, m2, and m3, and this is the three functions that we're going to find. So that corresponds to the unknown here. So that means we have to express the simultaneous linear equation by this form. Okay? Now, let's say, for example, to make our discussion simpler for discussion purposes, if we're going to set the system to be in equilibrium, so that means the acceleration of each of the particle I, so this where I is 1, 2, 3, and 1, 2, and 3 is 0. So that means we're going to assume first right now that this, and this is 0. Okay? And then placing these, the k and x terms to the left side, because this is the one that we are looking for. And then what remains in the other side would be the m and g. Okay, so you can do the simplification later, but these three equations should become, so equation number 1 should be written as k plus, this should be k1, and this is k2, okay? So k1 plus k2 x1 minus k2 x2 is equal to m1g. Equation number 2 becomes negative k2 x1 plus k2 plus k3 x2 minus k3 x3 equals m2g. And lastly, equation number 3 becomes negative k3 x2 plus k3 x3 equals m3g. Okay? So from here, we can actually write this equation in matrix form. So one way to do this is to align our equations. So let's say we're going to align this with M1 and G. Okay, as well as this one. And then we're going to align here your x3. So this is 0. This one should be aligned here. And then on this side, we're going to align x2. Okay, so this is your alignment. So our matrix equation becomes k1 plus k2, then minus k2, then 0. And then this is minus k2 plus k3, then minus k3, 0, negative k3, and k3. And this is multiplied with x1, x2, 2, and x3. And this is equal to g times m1, m2, and m3. Okay? So in this case, this will be our capital K vector matrix. This is your x vector, and this is your m vector. Then this is G. So this is your form. As I mentioned, this is now the solution to our x values. Okay? Okay? So let's have a quick example. So let's say M1 is equal to 60 kilograms. M2 is 70 kilograms. M3 is 80 kilograms. Sorry, this should be 80 kilograms. This is 80 kilograms. And then, let's say, let's make this K1 is 50 Newton per meter. Sorry about that. And then K2 is 100 Newton per meter. And K3 is 50 Newton per meter. Okay? Of course, if you want to substitute this here and then you solve your matrix algebra by this equation, you can do it as well. It's very easy because this is a very small, we have very small matrices. But let's say if you have a lot of matrices, let's say you want to solve Kirchhoff's rules in, let's say, in a circuit with, let's say, 100 possible loops. It's it's really difficult to solve this equation by hand. So what we can do is we can use MATLAB to do that. Okay,